Hello and welcome to the video. And until now, we saw that the key of proper operation of negative feedback amplifier is sensing the difference between the desired input or the desired value and the actual value. So we had a input Vi as a DC quantity, and for a constant Vi, output will reach K times Vi in a steady state. So the differential equation is a first half differential equation we got in our previous video, and this equation is same as of first order RC filter. And if we plot that RC filter or see the circuit, so equation comes out to be this, and this equation is similar to this. So the solutions which are given by this equation is basically this huge part where we had two parts of this equation, and we discussed about the solution to this equation in previous video. So like so far we have analyzed negative feedback with constant Vi, and let's see what happens when the input is changing. So until now we had a DC input, I mean constant input. So now there are two changing inputs we can analyze. So basically we have a step response, and the input varies from one particular constant to other particular constant, but both the steps are constants. But in another kind of response, which is sinusoidal response, so this kind of response is very useful to analyze the system, because any signal can be decomposed as a sum of sinusoidals. And if we know the response of our system to the sine wave, we can compute its response to any other signal. So let's start with the step response, and let's see the step response of negative feedback amplifier to the step input. So we have a step input where let's say from 0 constant voltage, it goes to Vx constant voltage, and we are providing it as a Vi to our system. So assuming initially at 0 volt, it is still a constant input and our system is at steady state. So V naught will also be 0 initially, and if V naught is 0, thus the V feedback will be, so it will be also 0 initially, and the error will also be 0 initially. Now what will happen is we apply a step of Vx, and the V naught still doesn't change instantaneously, and it will start from 0. So it is at 0, so it will not instantaneously change like a step, but it will start from 0, and VE will step up. So basically if it is starting from 0, then the feedback will also be starting from 0. So initially they are, let's say, at 0. So if feedback is at 0 and Vi is at Vx, so VE directly will step up at Vx, and thus our V naught will start to increase. And initially V naught starts increasing with the initial slope of omega u times Vx, and now as V naught increases, the V feedback increases, and thus the V feedback increases, so the difference reduces, so VE or the V error reduces, and thus the slope of V naught over here tends to decrease, and thus the slope of V feedback also tends to decrease, and this goes on until the slope reaches to 0 asymptotically, and V naught reaches to the new steady state. So this is how the system will behave to our step input. So we can say that this is how our response of Vin will look like, and at the same time it will go to, like, the V out response will go to K times Vx, but with a asymptotic relation. And similarly VE or the error will decrease like this. And if, let's say, this is the curve, and we have, like, for example, we increase the value of omega u, so the curve will look like the black dotted line. And we can say from our previous analysis in our previous videos that it takes 4.6 times time constant, which is k by omega u value, to reach the 99% of the steady state. And if we want to reduce the area under the curve, so basically this area under the curve, which is also corresponding to the energy. So let's say if you want to reduce it of V, we have to increase the value of omega u. and which will basically result in reduced energy and increased accuracy. So let's talk about the time constant, which depends upon the value of omega, but as well as the value of gain k. And let's take we have two different gains, and k dash is greater than k. So this will be the initial slope omega u times vn, and it will start with this slope. And initially v naught starts to increase with some slope omega u times vn in both cases, and later on when ve or the error voltage decreases, it starts depending on the value of k. So basically these two are the corresponding curves for the corresponding values of k and k slash. So basically time taken or time constant for k to reach steady state is lesser than for the time required for the higher gain integrator. So that's how it's related. And now let's talk about the second parameter or the second analysis, which is the response of our system to the sinusoidal inputs. So instead of time domain, it is convenient to analyze this kind of response in Laplace domain before analyzing the loop, the complete loop. Let's analyze how our integrator itself behaves in a Laplace domain. So this is our integrator presented in a Laplace domain. We have V in of S and V out of S. So basically we can say that our V out of S is nothing but omega u by S times V in, and our transfer function becomes omega u by J times omega. So the sinusoidal response can be easily explained by the Bode plot, and we have our function to be omega u by J omega, and which basically gives us the magnitude of omega u by omega, and it simply gives us a slope of minus 20 dB roll off. And due to the like the j present in the denominator, we have the phase always minus pi by 2. So this is how the response of our system will be, or not system, but the integrator will be. And based upon these outcomes, we will come back to the negative feedback loop, and we will place our integrator in negative feedback loop. So now we have an input of Vp cos omega t, and so we have Ve as the input to our integrator, and we know that Ve times our integrator is our output, and V is nothing but Vi minus V naught by K. So this equation comes out to be this value, and we never write our equations in this format. We have our analog template, so which is basically DC gain times the equation for poles and zero. So let's convert this equation by multiplying and dividing by this entity to make this equation in the analog template. And from this equation, if we make S equals to 0, we will get our DC gain, which is equals to K. And that's how we do our sanity check. And by looking at this equation, we will get our pole at minus omega u by K, and thus it lies in minus or the left S plane, which denotes that the system is stable. And now let's analyze the magnitude and phase plot of our system. So basically we have our magnitude of our system like this, and this is the angle of our system. So from this, we can say that at very low frequencies, this term can be neglected because the omega is very low, and thus h of s turns out to be k. So we can start from k, and when the pole occurs, it will start with the minus 20 dB roll off, and at frequencies higher than the pole frequency, omega is very high, and thus basically this 1 plus this value tends to be only this value, so 1 can be neglected. And after solving this, our magnitude comes out to be omega u by omega. So basically our phase will be starting from 0, and due to one pole, it will lag by minus pi by 2 and continue to go ahead. So I think that's all for this video, and thank you for watching.